Hi class, this is Dr. Selby here, and today I would like to summarize attractive forces. And the reason I'm not referring to these as intermolecular forces is I'm including ionic forces in this list. After that summary, I'm going to discuss Coulomb's law of attraction briefly in order to explain the relative strengths of these attractive forces for similarly sized particles. So first up are ionic forces, and ionic forces are the attractions between two oppositely charged ions. For example, in sodium chloride, we have an attraction between a negative chloride ion and a positive sodium ion. Of course, there's a lot of these attractions because they occur within many units in the crystal. And so that would be the ionic force, also referred to as an ionic bond. Next are ion dipole forces. Ion dipole forces are attractions between ions and polar molecules. They always occur whenever an ionic compound is completely dissolved in any polar solvent. However, in this class, the most important polar solvent is going to be water. And so in my example, I'm using sodium chloride, which does dissolve completely in water. And what we have is attraction between a completely charged, +1 charged sodium ion and the partial negative ends of the water molecules. And so with a black dashed line, I will draw in all of the ion dipole forces. Of course, in sodium chloride, we also have completely hydrated or dissolved chlorine ions, and the ion dipole attractions are between the partially positive H atom and the completely -1 charged chloride anion. And again, I'm just going to draw in those ion dipole attractions with dashed lines. Next, attractive force and also an intermolecular force are attractions between two polar molecules. And this is going to occur between all polar molecules. My example is formaldehyde, or H2CO. In H2CO, what I have shown here is the molecule, but also an electron density map. And the blue region means it's electron deficient. And the red region is very electron rich. So on formaldehyde, or H2CO, this region of the molecule and this region of another molecule, those are very electron rich. And this region of the molecule and this region of this molecule here is very electron poor. And this dipole-dipole attraction I'm going to draw in with a black dashed line is this. It's between those electron-rich regions of one molecule and electron-poor regions of another molecule. Here we have the hydrogen bond, and the hydrogen bond is an attraction between a partial positive H atom, for example, in water. I'm circling two partial positive H atoms, and the lone pair of electrons on a very highly electronegative O, N, or F atom. In water, of course, it's the O atom on another molecule. And so I'm going to circle this oxygen atom with one of its lone pairs. And so the hydrogen bond attraction, I'll draw in with a black dashed line, is here between that lone pair on the oxygen and that partially positive charged hydrogen atom. It's important to note while all molecules that can form hydrogen bonds also exhibit dipole-dipole forces, hydrogen bonds are stronger due to this directed nature and the shorter distance between the atoms involved. Recall the size trends. Oxygen, nitrogen, and fluorine are very small atoms. and they all have lone pairs. Here again, I'm showing the electron density map of water, and I'm just going to draw in a hydrogen bond with a black dashed line. The last attractive force I'm going to discuss is the London dispersion force. London dispersion forces are also known as van der Waals forces, or just dispersion forces for short. And what they are due to are temporary forces due to induced dipoles. They are the only attractive force between nonpolar molecules. They tend to be very weak for small molecules, and these forces increase with polarizability. What does that mean? Polarizability can kind of be referred to as electron flappiness, and polarizability is going to increase with size. It also increases with number of electrons, and these all go hand in hand. Number of electrons and mass. So you don't really have to think about polarizability being electron flappiness. You can compare the size of molecules, which for large sizes you're going to have a lot of electrons and a high molecular weight. So really large molecules can actually have large London dispersion forces due to their size or mass and the number of electrons because polarizability is greater. It's important to note that London dispersion forces or van der Waals forces occur between all molecules and atoms, regardless of their polarity. In my example, I chose a nonpolar molecule, I2. So I2 would not have hydrogen bonding or dipole-dipole forces. And on average, here I'm showing two molecules of I2. On average, a molecule of I2 is going to have an even electron distribution. That's why this is green, in the middle of the road area on this electron density map. However, electrons are constantly moving, and at one moment, electron density could build up on this side of the molecule. In doing so, that's going to make this area electron deficient because electrons move from one side to the other. What that will cause is an electron density to build up here to be attracted to this area. So this attraction is right here. And that is like our London dispersion force or van der Waals force. So these are temporary. So in the moment that these occur, you might have an electron distribution like this. And again, this is our temporary induced attraction known as the London dispersion force. So now I would like to discuss the relative strengths of these attractive forces and what they're measured by is just general physics, electrostatic attractions determined by Coulomb's law. And what this says in short form is that the strength of attraction, and they have to be oppositely charged particles, otherwise it's a repulsion, is proportional to, this means proportional, to the charge on particle 1 times the charge on particle 2 divided by the distance between them. So as the magnitude of these charges increase between these oppositely charged particles and the distance decreases, this strength is going to be stronger. So this is the reasoning behind the relative strengths of attractive forces. So here they are. And note, again, please, these are for similar size weight particles. So the strongest force, so here we're showing stronger going up, is your ionic forces. And the reason is because they're between two fully charged particles. So for example, in sodium chloride, you have a +1 sodium and a -1 chloride, and that is your ionic force or your ionic bond. The next one is ion dipole forces, and they occur again between one fully charged particle. So for example, I gave sodium chloride dissolved in water as an example. So we have a fully charged sodium here, and for the chloride ion, you have a fully charged chloride ion here, and then you have these partial charges on your oxygen end of the water molecule that are attracted to that full charge on sodium. So it's between a fully charged particle and partially charged particles or atoms in a molecule. Next, I want to skip down to dipole-dipole forces. So dipole-dipole forces occur between electron deficient and electron rich sides of molecules, and you can just think of those as permanent partial charges. And so the example I gave is between, for example, this electron rich oxygen and electron deficient side of the molecule, which is the hydrogen side of the molecule, and that was the dipole-dipole force. So those are not full charges. Stronger than the normal dipole-dipole force is the hydrogen bond, and it occurs between a partial positive H, for example, that partial positive H, and a very highly electronegative and small atom on another molecule that has a lone pair. And O, N, and F are the possibilities. And in water, of course, it's the O atom. And here I'm showing oxygen, and I'm circling one of its lone pairs, and that's the hydrogen bond. So this is stronger than a normal dipole-dipole force because it's directed. And those two water molecules are going to be closer together than, say, for example, these two formaldehyde molecules. So according to Coulomb's law, the closer together they are, and the stronger the charge is, you're going to have a stronger bond. So hydrogen bond is stronger than normal dipole-dipole. Last on the list, and again, I can't say this enough, we're comparing similar sized weight particles, because dispersion, to compare these, we need dispersion forces to be the same. Sometimes dispersion forces can add up to be strong forces in large molecules. So to compare apples to apples, these have to be similar sized weight, electron number molecules. So dispersion is going to be the weakest, and because it's temporally induced partial charges, or partial charges induced on the side of the molecule, or another way to say it is temporary induced electron rich end of one molecule with an electron poor end of another water molecule. This concludes this video. If you have any questions, please send me an email. Thank you and have a great day.